Too much. I was hearing all your smack talk. Okay. Welcome, welcome, welcome. Who kept you? The last tutorial?
Yeah.
I'll have a word.
No, I was asking a question. That's fine.
I'll still have a word with fists. Okay. So we're talking a little bit yesterday about limits and asymptotes. So I'm just going to recall that. So today we're going to talk about limits at infinity, and then we're going to talk about continuity. Limits at infinity. We have already seen, that's not an L, we have already seen vertical asymptotes which occur, when do they occur?
When x in the denominator is not included in the...
Way too much. There's a very simple explanation. Okay, so what's a vertical asymptote on a graph? Yes?
An infinite discontinuity.
Oh yeah, that's great. An infinite discontinuity, right? So the graph, if it has a vertical asymptote, is either doing this or doing this. So can anyone give me the algebraic description of that behavior? I know you can all do it.
Is it the limit towards the asymptote?
Okay, so yes, that is it. So we learned yesterday f of x has a vertical asymptote at x equals a when it is the case that the limit as x goes to a from the right of f is either positive infinity or minus infinity, or the limit as x goes to a from the left of f is either positive infinity or minus infinity. So either one, two, or both of these can be true to have a vertical asymptote. So I think so here's one that we found yesterday. I sort of gave you this equation, or this function, x minus 2 cubed plus 3. I just do that just so we don't use the same cubic over and over and over again. This is the standard cubic shifted 2 units to the right and 3 units up. So I draw that by just drawing the standard cubic. I know that the inflection point that normally runs through 0, 0 is now running through 2, 3. And then I just draw basically an arbitrary axis here. Even though, yeah, it should be the case that this is doing this. Okay. Where do we have why did I draw this? This was not the example that I wanted, but isn't it neat? Do something with no asymptotes. Okay, what I meant to write was this guy, 1 over x minus 5 plus 2. Okay, so this is going to be the standard 1 over x, but shifted right 5 units and up 2 units, so at least that part of my argument was correct. So we're going to see at this point, which is going to be 5, 2, that the behavior of this function is going to look something like this. Right, so I do dots because this isn't the usual coordinate axis. The coordinate axis is out here or something like that. I don't really care that much about it. Okay, so where is the vertical asymptote of this function? Yes, sir.
X equals 5.
Yeah, so you got this line here. This is x equals 5. If you take the limit from the right of 5, you get positive infinity. If you take the limit from the left of 5, you get negative infinity. That satisfies the definition for having an asymptote. So this has the horizontal vertical asymptote x equals 5. But notice, it also has another asymptote. Which one's that? Yes, sir. Yeah, you got this guy right here. And this guy is actually going to be the line y equals 2. So, but notice this also has, we also have a horizontal asymptote. Okay, at this time has to be described by y is equal to 2, this guy. right? Because as we look down the axis to infinity, we see that this is actually sort of limiting to it. So give me the algebraic description for what the horizontal asymptote should satisfy. Well, think about what tool I gave you, right? We don't actually have any ways of working with infinity. I can only use infinity in terms of using it to describe limiting behavior or in interval notation. So I'll start you off. If this is a function f, let's say, what is the limit of x goes to infinity of this function? As I send x down the axis towards infinity, right? If I walk towards infinity, what are we approaching in terms of y? 2, right? So this is 2. So this means that there is a horizontal asymptote at y equals 2. You actually see the same behavior at the other end. The limit of x goes to minus infinity of f of x is also 2. So we have a horizontal asymptote at y equals 2 at x goes to infinity. At x goes to minus infinity, right? So you can read it. So this is a nice little graph that demonstrates that you can have both horizontal asymptotes and vertical asymptotes. You should also note that it was only a coincidence that the horizontal asymptotes here were equal, right? You could have a function which has a different right asymptote than it does a left asymptote. Okay, so now we have to think about how to convert this to a definition that we can use. That's sort of less hand-wavy. So what's the definition of a horizontal asymptote? Which I'm just going to abbreviate to HA. Well, so f of x has a horizontal asymptote when the limit of x goes to infinity of f of x is L, or the limit of x goes to minus infinity of f of x is L. Okay? You have an asymptote if you have one of the two asymptotes. Right? You can always have an asymptote moving one direction and not the other one. Okay, but like what sort of I hand waved away here? What haven't we yet talked about? What haven't I yet given you rules for doing? Yes, sir.
Is it approach like from the left and right on the, like, you know how on the right side, like the positive side, positive?
Huh?
Can't you go left and right?
Left to what? Yeah, this is left.
Oh, okay.
All the way left, infinitely left. It's not left and right of this vertical line. It's when I say right, I mean go to positive infinity and tell me about the behavior. And if I say go left, that means go to negative infinity and tell me about the behavior. Which ends up being the answer to my yes, sir.
But they still have to be equal for the limit to exist, right?
No? What do you mean equal?
Like
These are two different limits. This is positive infinity. This is negative infinity. You can't approach infinity from the right. Okay, pause for a moment.
Got it.
I didn't tell you what approaching infinity means. I've only given you definitions, intuitions in geometry about approaching like a real point. Right? This is just the concept. So we have to talk a little bit about what it means to approach infinity, because you can't approach infinity from the right. You can't approach negative infinity from the left. Right? So we have to have different definitions for these. So I'm going to give you one more example, and then we'll talk about the definition. Or I'll talk about the definition in a bit. I want to show you at least one more function with a horizontal asymptote. Okay, so note. Did I skip a thing? I sure hope not. No, I will define it soon. So note, a function can have up to two different horizontal asymptotes. One for each side of the infinity. But here's another example. Let's look at the function y is equal to x squared minus 1 over x squared plus 1. I'm going to tell you that the graph of this looks like this. False. So this is going to be y. I have a point here, 1, 0. And this up here, this dotted line is y equal 1. Okay. So what does the geometry suggest about the horizontal asymptotes of this function? What line are we approaching as y? What line are we approaching as I run x to infinity? Y equals 1. So what does this suggest about the horizontal asymptotes? That that this is a horizontal asymptote, right? So geometry suggests, right, that the limit, let's just do this one, the positive infinity of that function f is equal to 1. Right? So how can we sort of demonstrate this algebraically? So algebraically, let's try to give a crack at this. And remember, we're restricted to only those limit laws that I gave you yesterday. So I'm definitely going to run out of room here, but let's just give her a go. So we have the limit as x goes to infinity of x squared minus 1 over x squared plus 1. I can't just put infinity in there, so what else can I do? Let's just try to simplify things. So this is okay. This is a strategy that I'm going to teach you about dealing with limits at infinity. So there's really only two behaviors you can have when you push x to infinity. What are the two behaviors? I've shown you one of them. So what is one of the behaviors as x goes to infinity?
Which is an asymptote?
Yes. Right? These aren't supposed to be trick questions. These are am I like making cogent sense? Right? Okay, so I told you, these are horizontal asymptotes. So one of the options for approaching infinity in x is to approach some asymptote in y. What is the alternative to that?
Approach infinity or negative.
Yeah, like either you're limiting to something finite, or you're not. You're growing, unbounded. Right? So either I can go to the end of this function and say, yep, it never gets bigger than this, or it just grows infinitely to either positive infinity or negative infinity. So what this means is that these terms here, I don't really care about anything but the biggest one. Right? Do I care? If I send x to infinity and square it, is it going to make any meaningful difference that I'm subtracting 1? No. I ignore it, basically. If I send x squared to infinity, does it make any difference that I'm adding 1 to that? No. As every grade school kid knows, infinity plus 1 is infinity. So we have a technique here where we're just going to isolate the largest terms, what I call the dominant terms, right? The ones that are going to blow up if you go to infinity. And we do it by doing this. You look at this and you try to find the, this is actually called the monomial, but the term with the largest degree, that is the largest exponent up here, and you divide by it, like this. You divide by the special one. Okay, so first, 1 over x squared over 1 over x squared. That's 1. I'm allowed to multiply things by 1. That doesn't change anything. Agree? Agree. Okay. So what else am I going to do here? Then I have x squared minus 1, and then x squared plus 1. And then what I'm going to do is I'm going to sort of simplify everything, but I need a new board. So I got to do that thing where it's boring. Think about how I can continue that and where you get stuck. Clean enough? Clean enough. Okay, let's continue. So I have that, and we're continuing. So what do I get? I get the limit of x goes to infinity. If I distribute that 1 over x squared through, I'm going to get x squared over x squared minus 1 over x squared. And then on the bottom, I'm going to get x squared over x squared plus 1 over x squared. Where does this take me? Now, I'm going to give you an insane amount of detail here. You're not supposed to give me this much detail on the midterms. I'm just going to show you explicitly that I'm using the limit laws. Now, the limit laws say that I can distribute this limit among additions, among divisions. So really, this limit applies to each of these terms individually in the following way. So first notice, what does this evaluate to? 1. This evaluates to 1. Okay, so on the top we have limit of x goes to infinity of 1 minus the limit of 1 over x squared as x goes to infinity over limit x goes to infinity of 1 plus the limit of x goes to infinity 1 over x squared. Okay, so what's the limit of x goes to infinity of something that's constant?
That constant.
Yeah, everyone else needs to understand as well. Okay, so if you can understand that the limit of a constant function is that number itself, then you haven't fully internalized the definition of a limit. Okay? We're talking about behavior here. How does the curve behave when I look really far down the axis? 1 is 1 everywhere. Everywhere. You pick an x, it's 1. Right? That's what the constant function means. So if the constant function is 1 everywhere, what is it at infinity? 1. Right? So obviously the limit of this function is 1. It's constant. In fact, the limit of any polynomial or rational function is just the evaluation of it. So this is going to be 1. This is going to be 1. Can we do this yet?
Yeah. Well, we can.
No, we can't. I haven't given you any rules for evaluating stuff like this. Not yet. Okay? Because I haven't given you any rules involving limits, terms to infinity, period. Right? So I can do this one, I can do this one, I can't do this one, I can't do this one. So somehow, at the moment, we're stuck. And we're stuck because I don't really know what this is. Any guesses? What are the two modes we're in right now whenever we're solving a problem? I've repeated these words 10,000 times. Yeah. Anyone?
We're confused.
Huh?
We're confused.
Okay, so I wrote down this. What kind of description is this? Is it an English description? It's an algebraic description. Okay. We have no idea how to resolve this algebraically. I haven't given you no algebraic rules. Will English help here? Maybe. Will geometry help here? Why don't we start there? Okay, so let's look at 1 over x squared. You know how that looks. That's this on the left-hand side of 0, and this on the right-hand side of 0. This is 1 over x squared. What does the geometry suggest about the limit at infinity?
Approaching 0.
Mm-hmm. I'm trying to get the back to answer. I need to know if you're just not answering because you're shy or you're not answering because there's a misunderstanding. Because then I need to undo the misunderstanding. So you can nod or just genuinely tell me that something doesn't make sense, and I'll do my best to unpack it. But you got to tell me. At least one person has to be honest with me and say, I don't understand this. So if you follow this line down to infinity, it goes to 0. Does that make sense, at least? Okay. Another way that we can describe this is look at this function here. Okay? I'm taking 1 over a number. So 1 over 2 is small. 1 over 3 is smaller. 1 over 10,000 is smaller yet. So if I go further down this axis, this number becomes smaller. Right? So if you put in a number like 10 to the power of a million, right? That's going to be very, 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 very small. It's very clear we're approaching 0 from both sides. Okay. So our intuition, so the geometric intuition suggests that the limit, well, it suggests basically that this is 0. Okay, that's what it suggests. Okay, and then we gave an English explanation as why that is sensible. But in mathematics, the English and the geometry are secondary supports for what ultimately has to be a strict algebraic explanation. Okay, you guys aren't responsible for understanding or even providing algebraic explanations of why the limits are the limit. All we expect you to be able to do is identify the limit and walk away. Okay, we're not going to ask you to prove that this is the limit because you don't have the tool set for that. Okay, so bearing that in mind, I'm just going to give this to you as a fact, right? Proposition. So proposition is kind of like, well, what's a theorem? Do you guys know what a theorem is? I've written them on the board like a bunch of times. So a theorem is it's like some statement about mathematics that's true under some preconditions. What kind of theorems have I given you so far? Squeeze theorem. Yeah, so I said, look, if you have a function and you squeeze it between two other functions, you can read the limit off of that. That's a theorem. A proposition is like a theorem, except it's like not important enough to be designated as a theorem. So when I write proposition, you can just regard it as, this is just a fact that I can use without really understanding why. Right, so the fact that I'm going to let you use is this. The limit of x goes to infinity of 1 over x is 0. Okay, and the proof of this, which is possible, I could work this out for you using the definitions I gave you yesterday, is omitted. And the proof will always be omitted, because this is not the proofs class. I just want to make you aware that in another version of this course, I could ask you the question, prove this. Right? Use the pieces of technology that I've developed for you and combine them in such a way that this is the result. So, given that this is a new fact, are we stuck anymore? Can we get this? How can we get this? I haven't given you a rule for 1 over x squared. I've given you a rule for 1 over x. Again, I'm trying, like if the obvious solution is the one I'm looking for. Yeah.
You could just the middle part out.
Yeah, exactly. So look at this. Note. The limit of x goes to infinity of 1 over x squared. That's equal to the limit of x goes to infinity of 1 over x times 1 over x. Yes? I gave you a rule yesterday saying that the limit is allowed to distribute over this product. So really what this is equal to is the limit of x goes to infinity of 1 over x times the limit of x goes to infinity of 1 over x. Okay, but I just told you what this is. So you're allowed now to, you know this as a fact. So now how do I finish this? This is 0 times 0, which is 0. So we are in fact no longer stuck, right? Because now we know what the limit of 1 over x squared is. It goes to 0. Right, so what am I supposed to write when we're unstuck? Aha. Okay. Aha. We're not stuck anymore. Okay, so I got to go back to this guy, which I'm going to designate as asterisk. Just a little word on this. You may see this pop up in my lectures and my handwritten notes. This means this is equal to the last thing that you see that was a star. So just go backwards in the notes and find the first instance of this, and that's what I'm just reusing like I'm doing now. It's just so I can say, and I'm continuing. So what do we get? We're going to get 1 minus 0 over 1 plus 0, which is 1, which ultimately was equal to the limit of x goes to infinity of what was the thing that I was talking about? This guy. X squared minus 1 over x squared plus 1. Does this confirm or dispute what we had postulated geometrically? Confirms it, right? We expected the horizontal asymptotes to be 1. That was our geometric intuition. We did some algebraic work, and we determined this, which is the definition for having a horizontal asymptote. All right, so maybe I should write that, which implies x squared minus 1 over x squared plus 1 has a horizontal asymptote at y equal 1. Just digest that a bit. Okay, so now I want you to think, what it means, I have to now give you a definition, a strict definition, for what it means to limit to something as x approaches infinity. So why don't you give that some thought? Try and see if you could write down in the strictest possible sense what it should mean to limit to L as x approaches infinity. Okay. Definition. I'm just going to say this is the definition of the limit as x goes to infinity. So anyone have any ideas? So what should it mean for the limit of f of x to be equal to L? Do you know what it means when I say L finite? Do you know what it means to be infinite? Okay, so finite is the opposite of that. 7 is finite, 8 is finite. Give me another number. Finite. The only thing that's infinite is infinity. But that's where the term comes from, right? So infinity actually is like the opposite of this term. Finite means to be like something that's non-infinite. Anyways. Whenever we write L as a real number, it's assumed to be finite. So maybe I'll just write that instead. That's maybe less confusing. So I'll just say L is properly a real number, and this R doesn't have infinity in it. Okay, so what's the strictest definition you can give me here? So what have we discovered from the geometry of the question? You gotta at least try. It's okay to be wrong. Right? That's the first step, is to just not care about not caring that you look stupid. That's how I got here. By irritating my professors by asking 100,000 clarifying questions. It's okay to ask me clarifying questions. Just give me literally any idea. Right? Or I'll flip the table. Some effort. Yes. Well, not you. Okay, why are we stuck then? Let's undertake the problem-solving framework. Because this can't happen on a midterm. I'm trying to coach you, right? So this is our coaching session. So we got to exercise a bit. Yeah?
Can you frame the question a little bit different? I'm not understanding.
Which aspect of it, right? Because I'm using this now because I strictly defined it before. So you got to tell me which component of this now is the thing that's confusing. Do you understand what a limit is? Do you understand what a mapping is? Do you understand what it means to be equal to a number? So this must be the problem. What it means to approach infinity.
It's the end behaviors of the function as it approaches L.
It's not, nothing's, well, f of x is approaching L. So this sort of is saying, as x approaches infinity, f of x is approaching L. That's another way that you can read this. Right? Don't try to visualize behavior at infinity. You can't visualize this is the visualization for x at infinity. Mathematics is a visualization in of itself. Okay, so you understand this, you understand this. Okay, so what does it mean for f of x to tend towards L?
To approach L, to become closer and closer to L, but not touching.
Yes. We have to become, when you say closer and closer and closer, I gave you a very specific word for this. Arbitrarily close to that limit. So this is better. With this exchange, we're going to learn a lot more. So please, who cares if your classmates think you're dumb? Right? Being dumb is the first step for gaining competency. You just have to accept it. Right? That I don't know what I'm doing, so I'm going to ask 10,000 questions. I welcome the questions. It's how I figure out where the holes are, and I'll try and correct them. So that was coach mode, because I want you guys to do really, really well. Okay, so I'm just going to write what you said, but mathematically. Or maybe we should start with English. Because that is entirely true. The limit of x goes to infinity of this function is equal to L when at least none of you are reading the solutions from the scanned sheets. That would be quite something. when there is some point what did I call it? Nothing. When there's some point on the x-axis after which f of x is arbitrarily close to L. Okay? So you're saying the behavior of this function at infinity behaves like this. That means, look, you tell me how close you want me to get to this limit, and I'll tell you how far along the x-axis you have to run down to start finding that behavior. Right? But it's the case that, so I'm going to erase this, so don't bother writing it. Or maybe write it, but I'm going to erase it. So here's this 1 over x, right? We're claiming that this is basically heading at infinity, like it's going to hit 0, but like not quite. So that means that someone can say, look, if you're claiming that this line becomes arbitrarily close to this axis, y equals 0, then surely you can get it this close, epsilon close, right? For epsilon, a tiny, tiny value. And that is the case, right? So notice if I strike a line here, and I say that this is x equal to a, if this point here, if this distance is already smaller than epsilon, everything farther down the line is just getting smaller, right? So if it's this small here, it's going to be even tinier. So if someone says, look, if the limit is 0, then your function should be at least 1 over 1,000 close to 0 at some point. And I can say, yes, it is, at 1,000. And beyond there, you'll always be that close. So you sort of have to just like struggle with the definition of it. But I'm going to give you the strict one now. Maybe that will make a little bit more sense. So definition, strict definition. I don't know why we don't show you these, because I think these are more sensible than the English descriptions, but whatever. So strictly speaking, the limit as x goes to infinity of f of x is L, okay, when, okay, for any tiny number that someone else gives you, there is some point on the real axis such that if x is bigger than a, then f of x minus L is small. Right, this is just basically saying the distance to L. Right, that's exactly what I was drawing here. That's that line. So let's look at this. They're saying this is sensible. They're saying, look, if you're telling me that the behavior at this function at very, very large numbers is L, then I'm going to say, look, you have to get this close to L. And I'm going to say, yeah, I can get this close to L starting here. And in fact, I'm getting even closer starting here and moving on to infinity. Right? So I can play this game with you. So for the limit as x goes to infinity of 1 over x, so this is how you'd have to prove it. We're not going to ask you to, but this is the game. If I claim that this is equal to 0, so someone give me a really tiny number. Tiny. 1 over a million. Okay. So you're saying, look, you should get, at some point, you should get this close to the limit 0. And I'm going to say, yes. So when x is bigger than 10 to the power of 6, we know that 1 over x is less than 1 over 10 to the power of 6, which is your epsilon. Okay, so you're saying, look, if you can get to 0, then you should be able to get 0.000001 close to it. And I'm saying, yes, I can get that close to it, provided that my x is sufficiently large. Right, so you got to think about that a bit. I'm not going to repeat it 1,000 times. I think it'll become more clear once we do more examples. As it always does. So stare at it. But again, we're not going to ask you to demonstrate anything. You have to just be able to read the behavior. Right? So you'll never have to give an argument as to why something is the limit. And it's much easier to determine what the limit is rather than prove what the limit is. So again, I'm just trying to give you intuitions about what you're doing. I'm never going to ask you to like reproduce these types of explanations. Yeah?
How does the line, like the arrow read in the algebraic definition? So like x,
This arrow?
No, the x is greater than a, and how does that, like, the arrow read? In the
Which arrow? That?
Yeah, like is there a double line in there?
Yeah.
Does that mean implies?
Inference, yeah. If the thing on the left is true, then the thing on the right is true. So be careful.
Is it absolute value of f of x minus L? I'm confused. Like, I don't.
Thank you. Then why did you?
That like.
Which for every tiny number is bigger than 0.
Yeah, it's the absolute value of the.
Well, let's start from the beginning. For every tiny number epsilon bigger than 0,
Yeah.
there is an a on the number line, such that every x after that a, it is the case that f of x minus L, the absolute, the distance to L from f, is tiny as well.
The distance from f L. So then it's.
This is f. This is what you're claiming the limit is. This is the distance to it.
Oh, and that it's always the absolute value.
I can't have negative distance.
Yeah. Okay.
That's what the absolute value function is for measuring distance.
That makes sense.
Yeah.
Yeah.
Make more sense? I'm just saying, if you claim that I'm this small, like there has to be a point where that property starts to hold from here and forever. But again, it's not too important you understand the strict definitions. You just have to sort of have a loose intuition about what is happening. So we'll do some more examples. But again, you are not supposed to understand everything I'm telling you. Right? This is just your first exposure to the material. After this lecture, you have to go home and restudy the notes and try out examples before understanding everything. I'm just giving you the way to look at the problems and the material when you go home. But you're not going to understand everything that I tell you. That's impossible. Right? I would need 10 times the amount of hours to like explain this to you in the sufficient amount of detail. So it's mostly on you to do the learning. Okay. So all of this may have been sort of difficult to understand, but the algebra of this, actually doing questions, is fairly easy, right? As long as you don't make silly like arithmetic errors. So here's an example. And this example is this. It's the limit of x goes to infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. Okay? So this is a rational function of two polynomials. Okay? And I want to investigate the behavior of this as x goes to infinity. So the one technique I've shown you is this technique of isolating dominant terms, right? If we're pushing all the values to absurdly large numbers. So we talked about this. If I put infinity in for x squared, subtracting 2 is irrelevant. I don't even care about that 2. I don't care about that 1. We've got to be more careful with indeterminants. So this is the whole purpose of the limit. I also don't care about this x and about this x. Why? Well, if I'm making these x's super huge, this one gets squared. Right? So it turns out that this one is growing way faster than this guy. So even though it's going to be like infinity squared minus infinity. I'm not supposed to say that. That's what the limits are. But so there is a real quick, I'm going to predict the outcome of this really long computation. My experience tells me the only thing that's going to matter when I run x to infinity is this term and this term. Those x squareds will cancel and what's left is 3/5. I predict ahead of time this is going to limit to 3/5. Okay? Now I'm going to show you all of the working that's going to demonstrate that. But like often I know the answer before even trying. Okay, what's the dominant term? X squared. Okay, so the limit, so this is equal to the limit of x goes to infinity. And notice that I'm writing this each time. So if I can do it on the board, you can do it on paper. I have to divide out by 1 over what? X squared over 1 over x squared. That's 3x squared minus x minus 2. This is going to be 5x squared plus 4x plus 1. Okay, let's continue. This is going to be equal to the limit of x goes to infinity. I'm going to now distribute this 1 over x squared into here. So I'm not going to write it again. So just pay attention. 3x squared divided by x squared is 3. Then we're going to get minus 1 over x. That's what minus x over x squared gives. And then minus 2 over x squared. On the bottom, we're going to get 5 plus 4 over x plus 1 over x squared. Okay. The limit laws tell me that I can place this limit individually on each of these terms. I'm not going to write it because that's a big waste of time. Okay, so you just see this limit now what's going to each of these terms. So once we do that, what's the limit of x goes to infinity of this constant 3? Okay, let's draw it. Here is the graph y equals 3. It's 3 everywhere. If I look down at infinity, what is the behavior? 3. You got to gain confidence, because if you're writing your midterm and you're spending all the time second-guessing yourself, you're going to run out of time. Right? So you also need to develop confidence in answering your solution so you could leave it and move on. Yeah?
So why can you like plug in the infinity now? Why couldn't you do it at the beginning?
Because I gave you a rule saying that you're allowed to. I said, assume from now on that the limit of x goes to infinity of 1 over x is 0. I gave you that. Like 3 blackboards. But you're right to say, how can we do this now? We can do it now because I gave you a rule. But that's good that you noticed, right? So yes, but I said explicitly, limit of x goes to infinity of 1 over x is 0. So now we can continue in this case, right?
No, that's not what I meant.
Okay.
You know how you factored out the 1 over x squared?
I didn't factor anything out. I'm factoring in. I'm distributing.
Okay, you're distributing it.
Yeah.
My question is, you're doing that so that now you can like plug in the infinity and see where it's approaching. Why couldn't you do that in the first step, like in the very beginning?
You get infinity minus infinity. You get infinity squared minus infinity over infinity squared plus infinity. So what's infinity divided by infinity? No. No. We'll talk about that in a second. But it's definitely not 1.
So
Okay, maybe I'll talk about that now. Right? Okay, so the question was, why not from the very beginning can we put x into here? Well, for one, infinity isn't a number. Right? You can't evaluate anything at infinity, but suppose we could, you would get 3 times infinity squared minus infinity minus 2 over, this is all like totally like nonsense what I'm writing, by the way. Infinity squared plus infinity plus 1. All right, so the question is, okay, so if I take infinity and I square it, I could have sworn I had like a whole list of these things. Huh. Maybe I missed out on it. Okay. There should be some definitions that I missed out on, but we'll talk about them. Okay, so there's some things that we have to discuss. Infinity plus infinity, infinity minus infinity, infinity times infinity, and infinity divided by infinity. You are never to write any statement. This is mathematical gibberish. This is illegal. This is why we have the limit definition. Okay. If I take the hugest number and then if I add to it, what do you get? Okay, so it is okay to say that this is infinity. If I take infinity and I subtract infinity, what do you get? No definition. Which infinity is bigger? Right? These aren't the same quantity. This is a concept. Okay? So conceptually, subtracting doesn't make any sense. Okay. If I take infinity and I multiply it against itself infinite amount of times, you're just letting infinity grow. Right? So this is also okay. This is fine. Okay. How many times does infinity go into infinity? Well, it goes in once, it goes in twice, it goes in 3 times, it goes in 4 times, it goes in an infinite amount of times. Okay? If something has more than one answer, we designate that undefined. Right? We're not allowed to have functions and operations that give us a bunch of different answers. Okay, so if we try to put in infinity in the first blush, you get a statement like this. So actually, the bottom is fine. But then you're screwed in the top because first of all, you have to do this, which is undefined. And then even if you were to resolve this, then the remaining quotient is undefined as well. Okay? So the whole point, as you indicated, of isolating these dominant terms is where are the infinities now? Gone. Right? They're gone. Well, they'll be in the bottom. I'm happy to let, like, infinity goes into 1 0 times. That much I know for sure. There's no room for infinity in 1. Okay, so this ends up resolving to the limit of x goes to infinity of, should not have written that. Okay, so remember those, right? Because if you ever get tempted to try to resolve the limit, and you say something like infinity minus infinity is 0, you're wrong. Okay, so we get 3 minus 0 over 5 plus 0 plus 0. So in the end, 3/5, which is what I predicted from the very beginning, using my intuition. Okay, I want you to, okay, so from now on, I'm going to write this once, but you should now assume this every single time I do an exercise. Check with Desmos. Okay, just confirm it. Confirm that the algebraic limits that I'm telling you are actually correct. Right? You should be able to plot this and look at it. You can do it now if you want. Oh boy. Yes, miss. Where the denominator will dominate the numerator.
Like there will be like a larger polynomial in the denominator than there is in the numerator.
0. So, okay, let's do another one then. This is just off the cuff. This is not in the notes. So it was asked, what happens? So let's just do this exact same example, but I'm going to remove this dominant term. So let's say now we have something like x minus 2 over 5x squared plus 4x plus 1. Okay, so my intuition tells me the dominant term is here. If I make x explosively large, this is the only thing that's going to matter. I predict ahead of time this is going to be 0. Okay, so I just undertake the same strategy. I divide by 1 over x squared, 1 over x squared. This is x minus 2. This is going to be 5x squared plus 4x plus 1. Continuing, we're going to get the limit of x goes to infinity of what? Going to distribute that. You get 1 minus 2 over x squared. Oh, sorry. You get 1 over x over 2 minus x squared. And then you get 5 plus 4 over x plus 1 over x squared. Using the limit laws, you get 0 minus 0 over 5 plus 0 plus 0 is 0, as predicted. You can confirm that by plotting with Desmos, too. That's the point of the limit. It's saying, look, we're talking about growth, okay? And here what we've discovered is that the growth of this guy and this guy are related by 3/5. We're saying that the growth of this guy is way less than the growth of this guy will go way faster than this guy.
If the numerator degree is bigger than the denominator, the answer is undefined.
Pardon me?
If the numerator degree is bigger than the denominator, would the answer be undefined?
Let's talk about that right now. I think that's where I'm heading. Okay, I'm gonna have to skip. I'm skipping an example. Please review it. So there is an example here. It was this guy. So do this yourself. So notice if I put infinity into here. Okay, the one thing I need to tell you before you embark on this, what's the dominant term? No. But you are correct to say that it's this guy. But this is the square root of x squared. So the dominant term is x. So just be careful. So you should try to conjugate this. That should be one of your first steps. So the solution's in the notes. This is going to be a worked example. I'm just running out of time. What else do we got? I'll skip that. Okay, so I'll give you another. So here are all the examples I'm skipping. Actually, I'm going to do one of the three parts of this. So the question is this. Here's an example. It's f of x is equal to 2x squared plus 1 to the half over 3x minus 5. Okay. This function has three asymptotes, two different horizontal asymptotes and one vertical asymptote. What's the vertical asymptote? The up-down one.
5/3.
Yeah, it's whatever the solution, like this can't be 0, right? So we have to make x cannot be 5/3, which means that there's going to be an asymptote at x equals 5/3. You'll have to confirm that by taking a few limits. But what I want to do now is just say, what is the limit as x goes to minus infinity? The minus here is an important distinction of this f of x, right? Of 2x squared plus 1 to the half over 3x minus 5. Okay. I just taught you this. What's the dominant term here? It's x squared, but that's itself square rooted. So the dominant term is the square root of x squared, which is x. Okay. So this is going to be equal to the limit of x goes to minus infinity. And then I'm just going to do this jazz where I say this, 1 over x over 1 over x. Here it's going to be 2x squared plus 1 to a half. This is going to be 3x minus 5. Okay, so this is super important now. I want to now move this into here. Okay, so let's rewrite this so that it can move into here. And you know what? Just to make it more familiar, I'm going to do this. All right. So what do I have to do to get this into here? How can I rewrite this? Okay, this is like grade 10 high school. Yeah.
X to the negative 1.
Yeah, that is a correct rewriting, but how can I rewrite this in such a way that I can get it into here? Yeah.
2x squared plus 1 to the power of a half.
What? Okay. If I have the square root of 7, okay, and I have 2 out here, how do I get 2 inside? Right? Because this is the same thing as the square root of 2 squared times 7, right? 4 times 7. Is this really alien to you? What do you mean? This is basic rationalization. This is the most basic rationalization. You should have done 10 million of these in grade 10. You've never seen this book. This is definitely prerequisite, right? Yeah. How have you not seen this? This is deeply troubling to me. Yeah. Oh my God, that's the same thing. What do you mean you can't reverse it, right? Okay, so you know how to do this. Oh, everyone out, right? If we teach you to do something one way, you don't need permission to do it the other way, right? This is an equal sign. Right? You can move either way, right? You know, I'm telling you that now. If I tell you could do something one way, you could do it. You could reverse it, right? It's like a vasectomy. Oh boy. Oh boy. Well, let's see how this goes. Oh, my life is a joke. Okay, I got to get this guy into here. So how do I get it in? What did I do? What was the strategy?
You squared it and then put
Okay.
The thing over.
We need this.
Yeah, square root of something.
Yeah?
It just means the same thing.
There's a nuance here. Okay? What did I tell you this was? Or why did I do it like this? How do you resolve this? What's the answer here? What is this equal to? No. Yeah. This is a new thing. You guys got to have to remember. This is hugely important. So basically, this is equal to this, which is equal to this. Okay? So, if x is less than 0, the absolute value, the square root of x squared, when x is negative, is minus x. So that means if I'm approaching negative infinity, x's will be minus. So 1 over x has to get replaced with minus 1 over the square root of x squared. Right? Because the square root of x squared is equal to minus x for x less than 0. We are in the x less than 0 range. Okay. That was a lot more difficult than it was supposed to be. Okay, so here we have limit of x goes to infinity of minus 1 over the square root of x squared. That's, I guess I should put all of that in a square root. It's going to be minus 1 over x squared like this times 2x squared plus 1. This is all going to be over 1 over x, 3x minus 5. Okay, let's do our distributing. So we're going to have limit x goes to infinity. I can now combine these, so you're going to get a minus 2x squared over x squared, that's just 2, plus 1 over x squared. Down here, you're going to get 3 minus 5 over x. Continuing, we're going to get what? Okay, so again, you just have to look at this limit and just apply it to each of these terms individually.
Shouldn't it be negative to infinity?
Yes, it should be negative infinity. Thank you. Okay, so we're going to get minus root 2 plus 0 over 3 minus 0, which is minus root 2 over 3. Okay, so what have we found? We found that this guy, so there is an asymptote. There is a horizontal asymptote at y equals minus root 2 minus root 2 over 3. So again, confirm with Desmos, whatever. Use your computer. Okay? So here's one of the horizontal asymptotes. It's at minus root 2 over 3. There's going to be another horizontal asymptote at positive root 2 over 3, and the vertical asymptote at x equals 3/5. So you should work that one out. Okay. What do we got next? Limits at infinity. Okay, so I suppose I need to tell you then what it means to not be restricted by an asymptote. And then I really got to get Russian. So this is the last thing that I'm going to do for this. So you make sure to read the notes that I posted, because there's a few more examples that I'm not going to be able to cover. Okay, so we can say this. We have a notation. So just notice here, I'm just going to give you a simple example. Here's just a parabola. Let's say that this goes through 1, 2. That means this is the parabola x minus 1 squared plus 2. What is the limit of x goes to infinity of f of x here? Can you read it geometrically? Anyone from the back? If I push x to infinity, how big are we getting? Infinity. Just reminding you that you're all going to have to answer these questions a week from now, like on paper. So please practice now. I'm trying to help. Okay, so we're allowed to put infinities here because there's a limit. So these are allowed to appear, right? So what does this mean? This means that the function as x approaches infinity doesn't have an asymptote. That's the only other option, right? So this is what we call this growing unbounded. Okay, you can grow in both to positive infinity and to negative infinity. But the point is that you can't bound it, either from above or from below. So I need to give you a strict definition for what this means. So what does it mean when limit of x goes to infinity of f of x is equal to infinity? Well, English and strict, right? So English, this means f of x is growing unbounded to the positive infinity. Which means, strictly, that the limit of x goes to infinity of f of x, this is equal to infinity when you can pick any number as big as you want, and I can find a place on the x-axis such that if x is bigger than a, then f of x is bigger than y. That's what it means. That's the strict definition, which essentially just means this. You cannot pick y large enough to bound f of x. That's how you can read this, right? It's like, well, if I'm growing unbounded, that means if someone else picks a huge number, that I can find a place on the number line such that my function is bigger than that. Right? It's like this game you play with kids. Pick the biggest number, 10 million, 10 million and 1, infinity, infinity plus 1. Right? That's what this is the codification of that game. Right? It's saying your function is growing unbounded if this child's game can play out. If you're like, I pick this number, well, I'm still bigger. Well, how about this number? Well, I'm still bigger. Right? And that will play infinitely long. Okay, so just one example here. I'm going to use the forbidden board just so I can move things along. What is the limit of x goes to infinity of x squared minus x? Do it wrong first. What's the wrong way of doing this? Who said that? Yes, absolutely correct. This is the wrong way of doing it. Okay. This is equal to distributing the limit so this is infinity minus infinity, which is 0, right? No, wrong. Here's the correct way of doing it. Any ideas?
1 over x squared.
Nope. Yep.
Do limit x approaches infinity for x squared and then minus limit x approaches infinity for x.
That's what this is, isn't it?
Oh, yeah.
Yes, miss.
Maybe like limit x times limit x? Like,
I think I know what you're talking about, and you're right. What about this? What about the limit of x goes to infinity of x times x minus 1? That's equivalent, right? Yes, confidence, right? I just factored something. They did teach you can go in that direction as well, I think. Okay, so but this is limit of x goes to infinity of x times the limit of x goes to infinity of x minus 1, which is infinity times infinity, which is infinity. This is fine. Don't ever write stuff like this. I'm not supposed to. It just makes it, I don't know, more clear, but it's technically incorrect. Okay, so I'm going to give you a couple exercises. And then we got to do the second part of this lecture. How much time do I got left? I'll plow through it. Limit x goes to infinity. 3x squared minus x plus 4 over 2x squared plus 5x minus 8. And then I want you to do limit of x squared half minus 1 over x for the following limits. X goes to 0 from the right, x goes to 0 from the left, x goes to 2 to the power of 3 halves, and x goes to minus 1. Okay, so you do those. I'm going to wipe down the board, and we'll do the second part of the lecture. Oh boy, I got to write shorter lectures, you would see. Copy, and then... Okay, I may have to write less. But the full notes are online, so you're not going to miss out. It's just that writing stuff down on the board is really taking a long time. So you guys copy that down because I got to erase this stuff. And I can't move this board, which is why it's the illegal method. I already regret using it. Can I erase this? Okay. Let's just check this thing out, see if we're still going. Yep. A what?
Try writing on the tablet, and then it converts the PDF. You can kind of project it from your computer to the...
It's not. I can write faster on the board than I can write on a tablet.
Oh, really?
It's the writing itself which takes. I go back to slides, but then everyone didn't like that.
I mean, like when you're writing your notes, like to write it on a tablet instead.
Well, what would the benefit of that be?
Like, in
You
a
could erase
sense of,
things faster.
yeah, like you could
Oh.
write it on the tablet and then like beforehand, and then email it to yourself and it's kind of like a PowerPoint but written and projected. And
Yeah, I could also use the docs. I don't know. I like using it's the writing. I could, if you want that, I can go back to the slides.
Oh, okay.
I guess. Right. The point is I need to. So I thought about that, but then I need to figure out how to screen capture that. I'm recording these things, remember? So I could plug in, but then how am I supposed to record what's showing up? I was using my computer to record the screen. If I go into the projector, I can't recover that video. So most of this is the restriction that I want to have these recorded. And I'd like to continue. That's more valuable to me than the 2 or 3 extra examples I'd be able to do. But it's all written. You can go find it. Yeah. But that would have been the benefit of the slides. I could have gone way faster. It's not even really the writing. It's the erasing.
Yeah.
It takes forever. I need to hire a TA or something just to run around and erase everything. Yeah, I've tried exactly what you said. You'd be surprised how huge those PDFs get.
Oh, okay.
Yeah, they're like gigabytes big because they just save them as big images. Okay, we're going to do the second half of this lecture. I'm going to write way less. I'm just going to write the most critical stuff. But this is a pretty important topic, and this is the notion of continuity. Okay, there is an operative definition that I can give you here, which is going to work like most of the time. So basically, a function is continuous over some interval when you can draw it without lifting your pen. Has anyone ever told you this definition? Have you ever seen that, do you know the definition of continuity? Okay, well, this is the definition of continuity then, right? A function is continuous over some domain if you can draw it without lifting your pen. So here's some examples. Let's restrict it to the interval AB. Here's a function. So if I'm restricted to this domain, can I draw this function without lifting up my pen?
Yes.
Yes, confident answers. So here we say that this is continuous on A to B. Okay. Here's another guy. This is A, this is B. It does this, it does this. Okay, so can I draw this function without lifting up my pen? No. This is called discontinuous. And if I designate this point C, I can say this is discontinuous at C. Okay. So, this is the geometric and English intuition about continuity, right? Here's the English. Here's the geometry. Now we need the algebra, which is typically the hardest part to codify. So think, how could we codify the rules for being continuous? So the first step is yes, sir.
Oh, can I start?
Sure.
It has to include all the numbers between integers.
Pardon me?
It has to include all the values between integers.
Well, why are you designating integers as being special? What's special about integers?
We have to define it somehow.
Yeah, but why did you pick why not fractions?
It's kind of arbitrary.
Yeah, so that's usually an indication that that's the wrong direction. If you're just throwing arbitrary things into your definitions. It shouldn't be arbitrary. It should be removing it should be crucial. Like, it should break everything. So I would first recommend that you don't actually try to give me a definition for what it means to be continuous at all points. Right? We should specialize the problem a bit and try and figure out what it means to be continuous at a single point on this function. Okay, so I'll tell you that. And I'll motivate it a bit. Okay, so given what I've told you about continuity and discontinuity, is this continuous? No, right? I have to draw and then lift up my pen and then continue drawing. If this was in here, would it be continuous? Right. So what was the difference between those two scenarios? The point was defined. Okay? So what if I took this out and then put a defined point here? Is this continuous? But it is defined. So what two things do you need for this function to be continuous? At A, here. Okay, so you identified this as being discontinuous. When I filled this in, you identified that as being continuous. Right? So you at least, if this is f, you need at least three things. F of A is defined, okay, which basically means A is in the domain of f. You also want the limit of x goes to A of f to be equal to f of A. Okay? So there's a limit that goes to here. There's a limit that goes to here. So the limit of f at A is here. Okay? So this point is removed. So the function is defined, but the function is not what it's supposed to be. Right? We have the point, but the point should be here. Right? So the definition that we need is that a function is continuous at a point is continuous at a point A think I said A. Yeah. When, and here it is, when the limit of x goes to A of f of A is equal to, whoops, the limit of x goes to A of f of x is f of A. Okay? That means if I'm walking along the curve, at every point of the curve, it's so is this continuous? I already told you no, but why is it not continuous given that definition? What does it violate? Yeah.
Because the lower point isn't being approached on either side.
Yeah, well, strictly speaking, it is not the case. The limit of x goes to A of this function is here, and this is not equal to this. It outright violates the condition that we wrote. So I just want you to keep in mind here that there's three things that are hidden in here that have to be true. All right, so notice. All right, so consequently, in order to show f is continuous at A, at x equals A, you have to show three things. Show three things. One, that A is in the domain of f. Two, that the limit of x goes to A of f of x, okay, exists. Three, the limit of x goes to A of f of x is equal to f of A. Okay? But really, there are three things that there's like a hidden, this one line is compactly saying these three things. That's sort of the nice thing about math, is you can get a lot of expressions, well, you get a lot of things that are expressed in small time, or small writing. Okay, how much time do I got? About half hour? Okay. Okay, so I'm just going to do one example. I'm going to skip a bunch of them, but this one's important, I think. Okay. Oh, be careful when drawing this. So it'll be y equals 4. Here I'm going to do y equals 2. I'm going to designate 3 spots, A, B, and C. I'm going to designate, and we're going to do this. Whoops. That should be open. This should go off. It should be like this. Okay. So I have 3 parts. We have 3 places on the x-axis here, A, B, and C. Notice that I wrote A, B, and C, and not 3, 6, 7. Because I don't care. Just 3 numbers that you pick. Right? So you shouldn't get scared when I use indeterminates rather than numbers, right? Because these are just standard values for numbers. Where is this function discontinuous? Yes.
At B and C,
Why is it discontinuous at B?
because you started the function already, and then you.
That's intuition. You got to give it to me strictly.
Oh, I see.
But what does it violate?
The limit. It's not approaching the same number on both sides.
Okay. So there's a discontinuity at B because the limit there doesn't exist. Right? It violates 2. Okay? The function's defined. There's a left limit and a right limit, but the limit itself doesn't exist. So that's for B. So fails 2. Okay. What about A? What does it fail? Yeah. A is not in the domain of F. So it fails 1. Okay, what about this one? Well, the function's defined, the limit's defined, but
It does not equal it.
they're not equal, right? it's obvious. In order for this function to be continuous, this thing should be here, right? If I put this back, then it would be continuous, right? So this fails 3. This is actually called a removable discontinuity. But a removable discontinuity is one that you simply can put back and it fixes everything. Right? Because sometimes we generate holes by dividing. And it's nice to put them back. But again, if you can just remember that a function is continuous on an interval, if you can draw it without lifting up your pen, that operative definition is good enough. But if we ever ask you to demonstrate something is discontinuous, don't give me hand-wavy English. All we require of you is to demonstrate that it fails one of these conditions. Right? That's much easier. Right? You say, look, this isn't discontinuous because this A is not in the domain, right? So your definition tells me that it excludes this. Don't give me a fairy tale. Okay, I'm going to skip some examples, so you just look at them. This one is one that I do want to look at. So there's a little nuance here. Is this function continuous at A? Why? Pardon me? I guess it fails the third, but it also fails 2, right? So, okay, but it is the case that if I go from the left, that the limit and the dot exist. Coming from the left, it's okay. Coming from the right, it's not okay. So for this scenario, we actually designate 2 other terms, and those two other terms are right continuous and left continuous. All right, so right continuous is when the limit of x goes to a from the right of f of x is equal to f of a. And left continuous is when the limit of x goes to a from the left of f of x is equal to f of a. Okay? So you see this is left continuous. Did I get my things right? Yeah, approaching from the left. This is left continuous, but not right continuous. Right? So this example, so I'll probably say, like I'm going to abbreviate this to L, cont, R, cont. So here, this is left continuous. Okay, not right continuous. Here's a question. If a function is continuous at A, is it left and right continuous at A?
Yes.
Raise your hand. Yeah. Yes. Anyone else? This should be very obvious, right? So if you're continuous here, obviously you're left continuous and right continuous. So a function that is continuous at A is also left and right continuous at A. These aren't separate categories, right? Something can be 2 things, right? So is it the case if you're left and right continuous that you're also continuous? Yes, because that's the definition almost. Yeah. Oh, okay. Okay, so now I can give you the definition of continuity in an interval. Okay, so I told you what it means to be continuous at a single point. So it's very easy now to take it and to expand it to intervals, right? So f is continuous on this interval when, okay, for every c in the interval, f of c is continuous. Okay, so notice here, I have open braces. Okay, so far, you can't include the endpoints. Right? Nothing's continuous at its endpoints. However, I just gave you this definition of right continuous and left continuous. So, moreover, if f is right continuous at x equals a, the left endpoint, and left continuous at x equals b, then f is continuous on the closed interval. Right, so what this is basically saying is that if you have an open interval a to b, you have to be able to draw the function without lifting up your pen. It's exactly what we said geometrically. So normally we exclude these, but you can also fill it in. Right? So this provision down here is saying, well, you can place your pen here. We won't worry about what's happening to the left. We won't worry what's happening to the right. But this is the definition for being continuous on a closed interval. Is this function continuous on the open interval a to b? Think. Tell me by the time I erase. I ordered a special cloth that's supposed to clean blackboards way better. So we'll see how that goes, if it even arrives by the end of class.
Is it a shamrock?
Shamrock?
You ever heard of that?
No, I know. ShamWow.
Yeah.
Oh. No, that's an infomercial type of thing, right? ShamWow.
It's the guy who did the slap chop, too.
Oh God, that guy?
He did a lot of cocaine. He did.
Well, we have that in common, then. Oh, I'm just joking. I'm just joking. It's not my favorite drug. This is continuous on A and B. Look, I can start here. I can draw the whole thing without lifting up my pen. It's really as easy as that. Well, it's easy as that to determine continuity. To show something is discontinuous, you actually have to give a structured argument. Omitted. Okay, so I just want to mention a couple things. When I say polynomial, do you know what that means? Really? Give me an example of a polynomial.
X squared plus 5x plus 2.
Okay, is a line a polynomial? Is a cubic a... What do you mean it can be? It is a polynomial. Every line is a polynomial.
Y equals x, isn't that mono?
Y equals x is a polynomial. Yeah.
I thought the definition of a polynomial was that it has multiple terms.
No.
No?
Is 0 a polynomial? Yes. When I write things down, things are allowed to be 0. Things can disappear just because I write a to the I, x to the I. AI is allowed to be 0. Those things can disappear. Okay, anyway, so a polynomial is this. I'm going to write it down for the last time. Okay, a0 plus a1x plus a2x squared, and so on. And then you got to stop, right? And then all of these a's are real numbers, and some of them could be 0, but maybe not that one. Okay, this is a polynomial, so recall a polynomial. Okay. Polynomials are everywhere continuous. What else do we got? Here's another theorem. If f and g are polynomials and what am I missing here? Yes? What? I thought you said Paul. Where am I missing? Yes. F and g are polynomials, and that means f over g is a rational function then f over g is continuous everywhere on its domain. Okay, why am I telling you this? Well, there's some rules in your textbook or online about like taking function compositions or adding continuous polynomials. So two functions that are continuous, their sum is continuous. Two functions that are continuous, their product is continuous. Their division is continuous provided that you're not dividing by 0. So if you ever have to argue something is continuous, you need a starting point. Your starting point is this. Every polynomial that you can write is everywhere continuous. Rational polynomials are continuous in their domain, right? So this will have to be your starting point most of the time. I don't think I can really demonstrate to you that sine and cos, these things are continuous without a lot of work. But anyways, so here are some starting points. Okay, so how much time do I got left to do the most important thing? Okay. 13 minutes? Okay, so the most important thing today is this thing called the IVT. The intermediate. It's not hard. Value theorem. Okay, so first of all, you better bet, period, if I give a theorem a name, that you're going to get tested on it. Things that get names are important. Okay, so you remember how we talked about continuity, and I gave you like an operative definition. I said basically a continuous function is something that you can write or draw without lifting up your pen. The intermediate value theorem is basically this. Says basically okay. So suppose we have a function and we have that f of a is less than 0 and f of b is positive and f is continuous on a to b. Okay, so what's the situation we have here? Okay, I have y equals 0 here. Okay, I have a here. I have b here. I know that I have one point a, f of a, that's below this line. I specified it was negative. I also have another point here, b, f of b. Right, I specified that this was positive. Honestly, this is all the intermediate value theorem is specifying here. So, here's a continuous function running from this point to this point. So when I draw, what am I not allowed to do? Okay, so if I connect this dot with this dot, is it possible to do it without crossing this line? No. How could I skip this line? I'd have to pick up my pen. But that would make it no longer continuous, right? All the intermediate value theorem says is that you can't connect these two dots without passing through this line. That's it. It's a little bit more complicated than that because I centered it at 0, but I'll write the general statement using the forbidden board. Okay, but if you're confused by IVT the first time around, I don't understand why. It's a very simple concept. Right? If you have 2 points and you have to write a line between them, they have to like obtain all of the y values from one to the other. Okay, so I'm going to write this now, the actual definition. Maybe I should flesh this out a bit more. Okay, so what we actually found here is a point C. So there exists C in the interval AB such that f of C is 0. That's what we have found. I don't know what it is. I know it exists, which is good enough. Okay, so here's the exact statement of the intermediate value theorem. Okay? You'll definitely be tested on this. Okay? So when you use a theorem, I always liken it to like crossing a bridge. You got to pay the toll before you can cross the bridge. So here's the toll. So the tolls are always expressed with this provision. So provided that you have these two things, f is continuous on a to b, closed, and then n is some number trapped in here from f over a to f over b, then, okay, so provided you paid this toll, the bridge you get to cross is this one. There is definitely a number in this interval such that f of c is n. Okay, so this is a little bit different than crossing through 0, so I'll explain what this means geometrically. Okay, so here's the intermediate value theorem. It says this: you have a line. This line is designated as y equal n. Okay, you have a point. So the number line is elsewhere, but here's a. I should really draw an axis then. Okay, so you have a, you have b, you have n. So this point and this point are at a and b. So what am I saying? I'm saying, well, let's suppose we have, well, n has to be in this interval. So if I put it in here, it's going to be bigger than this and less than this. So I have some point here, a f of a, and I have some point here, b f of b. Okay, so you see n is in between fa and f of b. The intermediate value theorem just says you can't connect these two dots without passing through this line. That's all it says, right? So if I pass these, so it says, look, if you have to connect this dot with this dot without picking up your line, you're going to have some point here, c, right? So intermediate value theorem says, right, there is some number c such that, well, there is some c in this interval, a to b, such that the function obtains the value n, right? Which is just a little bit more general than what I wrote there. And I'll send you off with this example. Okay? Show f of x is equal to 4x cubed minus 6x squared plus 3x minus 2 is equal to 0 has a root. Okay? What does it mean for a function to have a root? Yes, sir. Pardon me? That's correct. Could you give it to me as a sort of algebraic definition? So he says it crosses the x-axis. So that means that the function has to be 0 at some point. Yeah? So this has a root. So if there exists, I have to give you has a root in 1, 2. Okay? So this has a root in 1, 2, provided there is c in 1, 2, such that f of c is 0. Okay? So that's the. So if I asked you this on a midterm, show f of x, this f of x has a root, and you get stuck, I bet you if I asked you this question instead, show me there's a c in this interval such that f of c is equal to 0, you would be able to get that. Yeah.
And 1, 2 is an open interval.
Your 1, 2 is an open interval. Yeah. Doesn't really matter. We're not really choosing at endpoints. Okay. So how do you resolve this in the last dying minutes of this class? What do we have to do? Yeah.
Show between 1 and 2 there's a point over the x-axis and below the x-axis, so positive.
That's correct, right? So I told you that every polynomial is continuous. So we check off that box. This is continuous everywhere. So it's certainly continuous in 1, 2. You have to write that on your test paper. Right? So note, okay, f of x is continuous on 1, 2, right? Because it's a polynomial. Okay? You have to at least write this part. You will be getting a mark for that. I don't care really about the justification. Okay, so now we need to find two places in this interval where f of x is what? One of it has to be negative, and the other thing has to be positive. Now, I'll just tell you, f of 1 is minus 1. And f of 2 is 12. Okay? So I know that this function goes from the point 1 minus 1 to the point 2, 12, and I can't lift up my pen. But, so note that I have that f of x is continuous on 1 and 2. I have that f of 1 is negative 1. I have that f of 2 is 12. And I have 0 is in f of 1 to f of 12. Right? Minus 1 to 12. So this is really the interval 1 to 12. Let me just do something silly since I can't use this board, which is why I made it illegal. So this is going to be A, and I'm going to do the second part here. So reverse. Okay, so f of x is continuous on this interval because it's a polynomial. We also found we know that there's a point where it's under the x-axis, and we know there's a point above it. So the situation at hand is sort of like this one. We have a point here, 1 minus 1. We have a point here at 2, which is 212. So the IVT says that such a point is going to exist here. So note this, therefore, okay, by the intermediate value theorem, you're also going to get a mark for this. Okay, you can't just say it exists. You're using a piece of technology to get that number. So therefore, by IVT, there is a number C in 1 to 2, such that f of c is 0, which means which means f of x has a root in 1, 2. Okay, so we never asked you to actually give it to me. We're just asking you about existence. We're going to give you a function where it will be hopeless to find the solution. This is why this is a useful tool. Sometimes mathematicians need to say, yes, this equation is solvable. I don't know what the solution is, but I know it's solvable. So, okay, there's a worksheet which walks you through one of these proofs. So you should just be doing the worksheets naturally. I hope you've been doing them. It's a good thing to do after lecture to ensure that you've absorbed all of the material. Yes, miss?
So are you saying that we could, like, given the question, we plot a graph to find the solution?
Nope. You just have to guess. Just guess. Find a point that's under and find a point that's over. I guessed, essentially. If f of 1 and f of 2 didn't work out, I would have tried other ones. Yeah.